Hello everybody. My name is Florian Rademacher. I'm a PhD student and research associate at the Ideal Institute of the University of Applied Sciences and Arts Dortmund. And I'm very honored to be able to give the first webinar of the Microservice Community's research group, which has the title Taming Complexity on Studying the Application of Model-Driven Engineering to the Design, Development, and Operation of Microservice Architectures. This webinar has the major goal to provide you with information about the research that we are conducting here at our research group in Dortmund concerning the application of model-driven engineering within or to the engineering of microservice architectures. Let me first introduce myself a bit more. As already said, I'm a PhD student in computer science, both at the University of Kassel and the University of Applied Sciences and Arts Dortmund, or short FA Dortmund, working as a research associate at the Ideal Institute of FA Dortmund, and my research interests comprise distributed software architectures with a major focus on microservice architecture, model-driven engineering, or short MDE, and software language engineering, which lies at the intersection of MDE and programming languages. My PhD thesis has the title A Language Ecosystem for Modeling Microservice Architecture and has been submitted 1.5 months before, and the majority of the contents that I'm going to present are actually directly originating from these PhD theses, but I will also go into some future work and some ongoing work that we're conducting that builds upon the insights of the PhD thesis. I'm also a member of the Microservice Community's communication group, so you may have received messages from me on the Discord server of the Microservice Community or emails via the mailing list of the Microservice Community. If you haven't registered to any of these venues, please consider doing so to stay in touch with the community and always receive the latest news, for example, concerning upcoming events by the Microservice Community. You may also have a look at the Twitter account of the Microservices Community, which is also linked here on this slide. Our research group here in Dortmund is named Smart Environments Engineering Laboratory, or short CLAB. It's also located at the Ideal Institute. Currently, it consists of approximately 15 research associates, of which 6 are PhD students, and we also have a bunch of scientific software developers who support us in our everyday work. The research group is led by Professor Dr. Sabine Sachwe, who is also Vice President of the Microservice Community. In our research group, we conduct applied research projects in areas like e-health, Internet of Things, smart city, and smart manufacturing, and we have a research focus on topics like adaptive user interfaces, artificial intelligence, MDE, and also software architecture in a broader sense. Before I'm going to present our research statement, I would first like to give a brief introduction into model-driven engineering. Model-driven engineering, or short MDE, is a software engineering paradigm that uses models throughout all or selected phases of the software engineering process. In MDE, a model is usually a software engineering artifact that abstracts from selected properties of an anticipated or existing software system. It can be created, maintained, and understood by humans, and it is semi-automatically or fully automatically processable by computer programs. And this latter characteristic actually leads to the common goal of MDE, which is to elevate the purposes of models from documentation artifacts to first-class citizens in the software engineering process. For this purpose, MDE comprises 2 major concepts. The first major concepts are modeling languages. They prescribe the set of well-defined models concerning the syntax and semantics and provide pragmatic means to construct and maintain valid models that adhere to the well-formedness definition of a modeling language. The second major concept are model transformations, which prescribe rule sets to derive one or more target artifacts from one or more source models. On this slide, you can also see an example of a modeling language, or actually a set of modeling languages, which is UML. We are quite frequently concerned with UML when we conduct software engineering in practice, but also in research. Then we have a UML-based model, which is a class diagram here on this slide as an example, where the student class extends the person class. And we also see an example model transformation, which is a code generation that transforms the class diagram into Java implementations. Code generation is in fact the classical example of model transformation, often perceived as one of the key drivers of MDE. Expected benefits of MDE comprise, for example, complexity reduction. So the introduction of supportive abstractions for selected properties of a software system and the provisioning of means to comprehend and manage these abstractions. And in best case, this complexity reduction allows us to or allows stakeholders to participate actively in the software engineering process, even if they do not have a technical background. So for example, we can provide domain experts with modeling languages that allow these domain experts to express their concerns towards a software system using terms they are familiar with. And then we can, for example, use code generation to integrate the intents expressed by the models into our working system if we want. Another expected benefit of MDE is a value increase of models, so the introduction of processing means for existing models to integrate them with additional phases of the software engineering process besides documentation. And we also can expect a quality increase if we, for example, automatically incorporate patterns, bug fixes, or best practices into generated code, or if we analyze models for quality attribute assessment. This brings me to our research statement. Our research statement is motivated by the insight that the engineering of microservice architectures is inherently complex along different dimensions. So, for example, we encounter an inherent complexity in the design of microservices. And typical design challenges comprise the correct identification of microservices, which are often driven by capabilities that originate from the application domain. And when we then have identified our initial set of microservices, then still the question is there on how to determine the correct granularity or the most appropriate granularity of microservices. If they are too fine-grained, then microservices need to interact frequently with each other, which can increase network load and decrease the performance efficiency of the running system. If microservices, on the other hand, are too coarse-grained, then this may counteract scalability. There already exist some design techniques that are frequently used in MSA engineering, like domain-driven design or short DDD. But often, especially domain-driven design, appears too complex and or not rigorous enough to practitioners. So they have their DDD models at hand, but then the question remains, how can they map the DDD models to actual running microservices? Typical implementation challenges are related to the technology heterogeneity that is fostered by MSA engineering. So in the sense of that you can have different programming languages in MSA engineering, you can have different databases, different frameworks to realize your microservices, and so on and so forth. And this technology heterogeneity can increase the risk for technical debt, can introduce additional maintainability costs, and also lead to steeper learning curves. In addition, it makes technology management more complex, at least compared to monolithic applications, given an increased set of potential technology variation points. And this latter characteristic brings me to a typical operation challenge that in MSA engineering, we have the necessity of additional infrastructure components like container orchestration platforms, service discoveries, and API gateways. And often these infrastructure components leverage diverse technologies with their own configuration requirements and profiles and life cycles, which increases the complexity and which increases the set of technology variation points where we need to actively manage the technologies applied in MSA engineering. A typical organizational challenge is that MSA fosters DevOps and a collaborative team culture, but both of these assume automation and an efficient sharing of knowledge across teams, like, for example, the sharing of knowledge about which microservices exist and how are their current APIs being specified. Our research statement is therefore to investigate the applicability of MDE means in the design, implementation, and operation of microservice architectures to effectively cope with the inherent complexity of MSA engineering. This research statement and the investigation of the applicability of MDE to MSA engineering seems quite natural because MDE, as already said, focuses on complexity reduction, whereas MSA engineering comes with an inherent complexity. To investigate this research statement, we defined two initial research questions actually. The first research question concerns modeling languages and asks, How do modeling languages for the application of MDE to MSA engineering need to be constituted to guide stakeholders in MSA design activities, to allow the management and selective application of heterogeneous technology information, to harmonize infrastructure configuration to facilitate the deployment and operation of microservices, and to foster efficient knowledge sharing within and across MSA teams using, for example, models that are expressed in concise modeling languages with terms or using terms that stakeholders in MSA teams are directly familiar with. The second research question concerns model processing and asks how can models which were constructed with the modeling languages be used besides architecture documentation to foster automation within and across MSA teams, for example, by the generation of boilerplate code and the generation of API specifications that are immediately consistent with this code. We also study a research question concerning metrics-based quality assessment, and we also want to allow technical MSA stakeholders, like for example microservice developers that do not have an MDE background, to implement their own custom model processors for their very purposes. Then we started to investigate research question 1, and our research approach was to first identify an initial set of modeling concepts. And back then, when we started the investigation of research question 1, there were no activities concerning the conceptualization of MSA engineering or MSA as such, because back then MSA was still mainly driven by practitioners, and there were no activities that aimed to identify the underlying concepts of MSA. Therefore, we, in this first step, modeling concepts identification, we performed a survey of conceptual frameworks for the broader area of service-based software architectures and also service-oriented architectures to come up with an initial set of concepts that is relevant both for service-based software architectures and MSA, which rely both on the notion of service, obviously. So we were suspected that the basic concepts were quite similar in both areas. Like, for example, the concept of a service, an interface, an operation, an endpoint, and so on and so forth. In a second step, we performed a concept refinement through an analysis of 7 non-trivial open source microservice architectures with the goal to really identify those concepts that are directly and immediately relevant to MSA engineering. And therefore, we looked at actual implementations of microservice architectures. In the third step, we performed a concept clustering based on the concerns and viewpoints of stakeholders in MSA engineering. Both this concern and viewpoint terms, they originate, or we understood them as defined by ISO 42010. Based on this concept clustering, we implemented our modeling languages using the Eclipse modeling framework, and then we validated the languages and also performed an empirical assessment of their quality and use. On this slide, you can see in more detail which modeling languages currently exist in our ecosystem. So the first one is the domain data modeling language, which allows to express the concerns originating from the application domain towards a microservice architecture. So it allows to model, for example, domain concepts that need to be realized by the microservice architecture. Then we have a technology modeling language that aims to make technology decisions explicit and allows the management of technologies in a microservice architecture. Then we have a service modeling language to express in a concise syntax the existing microservices, their interfaces, their operations, their APIs, and so on and so forth. Then we have a mapping modeling language, which allows to keep domain models and service models technology agnostic and reuse them across different technology models. So if you want to, for example, migrate a microservice from the Java programming language to the Go programming language, then you can use the mapping modeling language to exchange the technology models of both programming languages, reusing the same domain and service models. And finally, we have an operation modeling language, which aims to harmonize and therefore facilitate the configuration of the deployment and operation of microservices. Each modeling language belongs to a specific viewpoint. again, the viewpoint notion follows the definition from ISO 4210. And for the domain data modeling language, we have the domain viewpoint. For the technology modeling language, we have the technology viewpoint. For the service modeling language and the mapping modeling language, we have the service viewpoint, and the operation modeling language belongs to the operation viewpoint. And again, following the notion of a viewpoint from ISO 4210, there are a set of stakeholders that or whose concerns are actually framed by the viewpoints. For example, service developers and service operators, they construct technology models in the technology viewpoint using our technology modeling language. On the following slides, I would like to present some examples in the syntaxes of our modeling languages. And these modeling examples actually stem from a paper that we have published recently under reference 42. And within the paper, we introduce a platform for the management of charging stations for electric vehicles. And we also show how significant structural information of this architecture can be described using our modeling languages. Actually, for the examples on the following slides, I focused on one specific microservice from the platform, which is the charging station management microservice that is responsible for the management of charging stations and their related data. And in this listing here, you can see an excerpt of the microservices domain model, which is expressed in our domain data modeling language. So the model belongs to the domain viewpoint. In line 1, we define a context called charging station management, and the context keyword or the context construct of our domain data modeling language is directly inspired by the notion of a bounded context from domain-driven design. Bounded context in domain-driven design is an approach to define a scope or to cluster domain concepts that belong together, that change for the same reason, and to define a boundary around these domain concepts. And if two bounded contexts want to share information with each other, then this information sharing needs to be made explicit in the domain model. And here we define a context called charging station management for our charging station management microservice. And in our modeling language, this context can comprise different kinds of domain concepts. For example, structured domain concepts like the one defined here starting in line 2, which is called electrified parking space. It is an entity and an aggregate in the sense of DDD, meaning that it has an identifier and also consists of other structured parts. In line 10, we define an enumeration called charging type, and starting in line 11, we define a second structured domain concept called electrified parking space created, which is a value object and a domain event and is necessary to allow our microservices to interact with each other using or in an event-driven manner, in the sense that they exchange information asynchronously via a message broker and in the form of events. On this slide, you can see two examples of technology models expressed in our technology modeling language, so they belong to the technology viewpoint. And in the first model, we have a technology model for the CQRS pattern. CQRS stands for Command Query Responsibility Segregation and is a quite popular pattern in MSA engineering because it views a microservice as a logical unit that can be decomposed into several physical implementations. And each of these physical implementations is either a command side or a query side of the logical microservice. A command side microservice is responsible for handling command requests that can update the database of the microservice. And query-side microservices, on the other hand, are only responsible for reading data from the database. So we can decompose a microservice into units that are responsible for either writing data or reading data. And in our management platform, this pattern is applied because we have seen that query requests or reading requests are much more frequent than writing requests, and it allows us to scale the microservices that only allow database reads independently of those that only allow database writes. And the technology model for the CQRS pattern therefore defines two so-called service aspects in line 3 and 4. The first aspect is called command side, the second one is query side. And this aspect mechanism of our technology modeling language can be used as a metadata mechanism that allows to semantically enrich microservices and their elements with additional information. So for example, we use the command side and the query side aspects to mark a microservice as being either a command side microservice or a query side microservice following the semantics of the CQRS pattern. In the second example technology model, we have a model for Kafka, for the technology Kafka, for the message broker technology Kafka, actually, which we are using in our management platform. And this technology model defines the existence of a protocol called Kafka, which is an asynchronous protocol in a binary data format. And this protocol is used by microservices to interact with the Kafka message broker. The model also defines a service aspect in line 6 called participant. It can be applied to the operations of a microservice and can be used, among others, to define the topic by which the operation shall interact with the message broker and by which the microservice therefore interacts with the message broker and can send events to. On this slide, you can see an excerpt of the command-side microservices service model expressed in our service modeling language, so belonging to the service viewpoint. And the microservice is defined starting in line 10 using the keywords functional microservice. It also has an interface called commands, and in line 15, there is the start of the definition of a service operation called send parking space created event. It has a single asynchronous outgoing event parameter that is typed by the electrified parking space created domain event, which we have previously modeled in our domain model. And this is actually possible because our modeling languages integrate an import mechanism. So here we can, for example, import the domain model that we have constructed before and then use the model's domain concepts to type the parameters of our operations. Conceptually, this import mechanism allows the integration of viewpoints with other viewpoints. So here we conceptually integrate the domain viewpoint with the service viewpoint and can reuse information that we have previously expressed for the domain viewpoint or in the domain viewpoint. Similarly, we can also integrate the technology viewpoint with the service viewpoint by importing the previously modeled Kafka technology model. We can use the built-in add technology annotation to apply the Kafka technology to our microservice, which is done here in line 6. And in line 8, we use the built-in add endpoints annotation to specify an endpoint for the Kafka protocol, which is modeled in the Kafka technology model. In line 14, we apply the participant aspect from the Kafka technology model to configure the topic to which the send parking space created event operation shall send its events. In this case, the topic is named parking space created events. Similarly, we import the technology model for the CQRS pattern, apply it in line 7 to our microservice, and in line 9, we also apply the aspect command side from the technology model to configure our charging station management command microservice as being a command side of the logical microservice charging station management. On the next slide, we can see an excerpt of the command side microservices operation model, which is expressed with our operation modeling language and thus belongs to the operation viewpoint. Our operation modeling language follows the approach of containerized microservice deployment and therefore provides a keyword called container, which is used here in the model in line 6 to define a container called the charging station management command container. Next, we need to configure the technology that it shall be used by the container, and therefore we can import a Kubernetes technology model that we have prepared before. And similarly to what we've seen in the service model, the operation modeling language also provides an import for technology. So we again integrate the technology viewpoint and the technology modeling language, but this time with the operation viewpoint and the operation modeling language. So we can import this Kubernetes technology and then we can use the built-in add technology annotation to assign the Kubernetes technology to the modeled container, which happens in line 5. The technology model also defines a deployment technology together with an operation environment, and both of these information need to be assigned to the container so that the container is, so to speak, aware of the deployment technology that shall be used to run the container and to also specify the operation environment, which in this case refers to an image called OpenJDK 11 JDK Slim. In addition, technology models may provide configuration values or configuration properties for deployment technologies. And in this case, the Kubernetes technology model defines a property called port, which is assigned in line 15, the value 8071. And this actually is part of the harmonizing syntax of the operation modeling language to support as much as infrastructure and operation technologies that are out there for MSA engineering to provide a common syntax to configure these technologies and to make them usable within operation models, as I said, in a harmonized way or in a consistent way. Next, we import the service model from the previous slide. So again, we use the import mechanism of our modeling languages to integrate two viewpoints. And more specifically, in this case, we integrate the service viewpoint with the operation viewpoint by the import of the service model in line 2. And then we can use the deploys keyword of our operation modeling language in line 9 to specify that the charging station management command microservice that we've modeled on the previous slide shall be deployed using the modeled container. In addition, our operation modeling language also allows to import other operation models, and we can import the nodes that have been modeled within these operation models. And the node can either be a container or it can be an infrastructure node. So our operation modeling language also allows the modeling of infrastructure nodes, like, for example, service discoveries, identity managers, message brokers, and so on and so forth. And with the import of this operation model, we can actually use the keyword depends on nodes in line 10 of our operation model here. And in line 11 and 12 refer to infrastructure nodes that have been defined within the imported operation model infrastructure.operation. The configuration of node dependencies allows us to specify that the charging station management command container that we have modeled here actually depends on nodes that are called IDM, message broker, MongoDB, and service discovery, and that originate from the imported operation model. And using this syntax, it's possible to define that our container really requires the capabilities that are provided by these imported nodes. And for example, the microservice actually needs the message broker, so it must have access to the message broker, which is why the container also needs to or depends on the message broker to be there to actually be able to run the microservice within the container. On this slide, we summarize results concerning the language's applicability. So we found out in a study that our modeling languages have a higher effectiveness than UML-based modeling for MSA engineering. We also showed that our modeling languages allow the top-down construction of new and also the reconstruction of existing microservice architectures from heterogeneous domains and with differing architecture patterns and communication paradigms. If you're interested in the detailed results, please have a look at references 42 and 38. Next, we started to investigate research question 2. Research question 2 concerned model processing, and our research approach for this question was to first select initial and supportive model processing purposes for MSA engineering. And here we decided to investigate the classical code generation approach or the model processing kind of code generation in the context of MSA engineering. And we also wanted to focus on what can we actually do through static model analysis to assess the quality of modeled microservices and modeled microservice architectures. In the second step, we designed and implemented a model processing framework that allows model processor implementation for these identified purposes and through technical MSA stakeholders that do not have an MDE background, like, for example, microservice developers, which is likely that they do not have an MDE background. In steps 3 and 4, we validated the framework's applicability for code generation and also for static model analysis. When we applied the framework for code generation, we first implemented a so-called Java base generator, which is a code generator for the Java programming language that allows the basic mapping of modeled elements expressed in our modeling languages to Java classes. For example, modeled domain concepts from domain models are mapped to POJOs, and modeled interfaces from service models are mapped to their own Java classes. The Java base generator does not depend on a certain technology or does not target a certain technology besides the Java programming language, but it can be enriched with plugins, and we currently have plugins for CQRS, DDD, domain events, for the Spring Framework, and for Kafka. And these plugins are actually capable of enriching the AST that is provided by the Java base generator with, for example, additional annotations or additional configuration files. When we applied the Java base generator with all the mentioned plugins to the charging station management microservices command side, which we have modeled on slides 19 to 22, then we saw that we are able to reach a net ratio between manual model code and generated boilerplate code of about 4.49. So this basically means that we are able to generate 804 lines of Java-based service code from 179 lines of model code. So this makes us confident that our code generation approach is basically efficient, or that code generation as such is basically efficient for the implementation of microservices, at least when we have a look at general purpose programming languages like Java. And we are also confident that this effect can scale across microservices and across microservice teams, because microservices might be micro also in the sense that they do not have the most lines of code that you can find in your system, but still lots of boilerplate code is necessary if you want to, for example, connect your microservice to a Kafka message broker. So these results makes us confident that code generation is at least applicable for general purpose languages in the area of MSA engineering. We also have code generators for technologies like Docker and Kubernetes, MariaDB and MongoDB. For Eureka, we currently also have a code generator for Keycloak, which is work in progress. And we also have a code generator for Zool. When we applied the framework for quality assessment through static model analysis, we first surveyed 4 metric suites which are applicable to MSA engineering. And based on our results from the survey, we implemented a static model analyzer that supports 20 out of 26 metrics from the suites. So we can apply the static model analyzer to models expressed with our modeling languages and then gather results for 20 out of 26 metrics that are usable in MSA engineering. Based on these metrics, we are nowadays able to assess the cohesion of microservices based on, for example, the similarity of interfaces, messages, and domain objects. We can also assess the complexity of microservices based on structural microservice characteristics, state management, and interaction dependencies. And we also have a heuristic which provides us with a lower bound size assessment for the message size of a microservice. All in all, we consider the combination of our modeling languages, the model processing framework, and model processors an ecosystem for model-driven MSA engineering and call it LEMMA, which stands for Language Ecosystem for Modeling Microservice Architecture. And LEMMA is actually our research prototype on which the PhD students in our group and other research associates are actively working to study the application of MDE to MSA engineering, both from a conceptual and theoretical perspective, but also from a practitioner's perspective. In the last part of my presentation, I would like to present to you some selected ongoing and future work that either uses Lemma or builds upon Lemma. The first work that I would like to present has been quite recently published as an article in Springer Nature Computer Science and is available in the form of an open access publication. So if you click on the link here on the slide, then it navigates you directly to the article and you can immediately have a look at the details in the article when you're interested in what I'm now going to tell you. The title of the article is Applying Model-Driven Engineering to Stimulate the Adoption of DevOps Processes in Small and Medium-Sized Development Organizations, and it presents results from a recent study of employing Lemma, thus MDE, for MSA engineering in small and medium-sized organizations, or short SMOs. The motivation for the article came from insights that we gathered from a secondary analysis of interviews that we have been conducted for a previous comparative multi-case study with 5 professional software architects that are responsible for microservice architectures and SMOs from our partner network. The first insight from the secondary analysis was that OpenAPI in combination with Swagger is the most prominent approach to specify service APIs and the only one to document APIs for these very SMOs. The second insight was that the configuration and maintenance of deployment and operation infrastructure is often too complex for cross-functional teams, and thus SMOs tend to delegate the responsibility for the configuration and maintenance of deployment and operation infrastructure to dedicated operation teams, which contradicts MSA's ownership principles. So instead of having true cross-functional teams following the DevOps philosophy, including developers and operators, SMOs tend to establish dedicated operation teams that are also responsible for the deployment of microservices that are delivered from the real microservice teams, so to speak. The third insight is that besides one case, API specifications are not collected and providing using a centralized system, but exchanged upon explicit request, like for example, emails between teams. So if one team needs to know the API specifications of another team's microservices, then the first team has to actively contact the second one to get access to these API specifications to be actually able to implement microservices that are capable of interacting with the microservices of the other team. The fourth insight was that SMOs consider the establishment of a common architectural understanding important, but they usually lack human and time resources to tackle this challenge in an appropriate manner. Actually, as soon as the software system of an SMO becomes a success, then SMOs tend to invest more time into the establishment of a common architectural understanding among teams, often because they are then it is possible to actually get the human or the time resources to tackle this challenge. But especially at the beginning of the development of a new software system, the establishment of common architectural understanding is not pursued by SMOs. Based on these insights, we proposed a lemma-based workflow to foster and to stimulate the DevOps adoption by SMOs. With this workflow, teams first derive lemma domain and service models from OpenAPI specifications using an automated model transformation. So if teams already have their OpenAPI specifications at hand, then they can put them into an automated model transformation and gather the corresponding lemma domain and service models from the specifications, thereby distinguishing between the domain perspective and the service perspective on the microservice architecture, which also allows us to analyze these different perspectives independently of each other if we want. And actually, the usage of models also allows us to apply all the classical MDE means that there exist, like code generation, like static analysis of models, and so on and so forth. So translating OpenAPI specifications to lemma domain and service models open up the gate, so to speak, to apply MDE means to these specifications to gather further insights from them, for example. In addition, teams can then accompany the derived models with operation models using the harmonizing syntax of Lemma's operation modeling language, for which we have seen an example before. And then they can, for example, generate technology-specific deployment and operation configurations from the models. With this step of the workflow, we aim to empower the teams in SMOs to also specify the concerns towards the deployment and operation of their microservices, even if the deployment and operation infrastructure is complex. In another step of the workflow, we also propose that all team-specific models are finally collected centrally, and model processors then gather information to foster a common architectural understanding among teams in an automated manner, like, for example, visualizations of service APIs or service dependencies, and all teams have immediate access to the gathered information about the architecture. For example, this can happen by teams committing their models into a version control system, and then a model processor can be activated to actually retrieve the necessary information and then provide other teams with this information to foster common architectural understanding, like, for example, these visualizations of service APIs. We validated the workflow and its implementation for a complete case study architecture, and in future work, we are currently actually planning to perform an in-depth evaluation with more case studies from SMOs. Another ongoing work that builds upon Lemma is model-based microservice architecture reconstruction. This work is motivated by the insight that MSA fosters team independence, but starting from this characteristic of MSA, microservice architectures are particularly exposed to deviate from an anticipated architecture design over time. So software architects or a team of software architects might come up with an architecture design for a microservice architecture, but since microservice teams are, for example, free to migrate their services to other technologies or even publish new services as they work on the system, the anticipated architecture design is likely to deviate over time. This is also motivated and driven by the fact that one microservice might change its anticipated interactions with other microservices as the system grows. Therefore, we consider the study of the application of semi-automated or fully automated approaches to software architecture reconstruction, or short SAR, a sensible undertaking in the context of MSA. Lemma's modeling languages seem expressive enough to reconstruct significant structural information about microservice architectures, as we were able to show in a recent work published on reference 38. And therefore, one of our current works actually aims to automate Lemma-based SAR using static analysis of microservice artifacts like the aforementioned API specifications, but also source code and so on and so forth. However, to be able to reconstruct significant information about a microservice architecture, we need to extend Lemma with constructs and or languages that allow us to express the dynamic information about microservice architectures in future works. Currently, we can express structural information with Lemma, but we're kind of weak concerning the expressiveness of dynamic information about microservice architectures, like, for example, service level behavior specification or architecture level process specification. So if we want to allow the model-based reconstruction of microservice architecture information, then we also need to heavily consider the dynamic behavior of microservice architectures. The last work that is sort of a more future work that we're currently reasoning about is the quality-driven microservice architecture engineering. Currently, Lemma's static analyzer, as described before, supports the assessment of service and or architecture cohesion, complexity, and size based on different metrics. Cohesion, complexity, and size target the maintainability quality attribute. However, we believe that the static analysis of Lemma models might also contribute in the assessment of the portability and compatibility quality attributes. In addition, Lemma's integration with existing model-based approaches for performance analysis should be sensible to assess the performance efficiency of services and or architectures. So in future works, we would like to extend Lemma's static analyzer with support for further metrics of other quality attributes than maintainability. And in a second step, we want to provide Lemma users with IDE support to assess quality at the time of model construction. As described before, Lemma has been implemented atop the Eclipse modeling framework. So the Lemma modeling languages are actually plugins to the Eclipse IDE. And it would be sensible to provide Lemma users with a dedicated IDE plugin for quality assessment, so that when they construct, for example, a service model using the Lemma's service modeling language, then a dedicated view in the Eclipse IDE could tell the modeler how well the model performs, for example, in terms of cohesion or complexity. In a third step, we could then combine this quality-driven MSA engineering with code generation to retrieve a quality by construction approach for MSA engineering, meaning that when the dedicated quality view in the Eclipse IDE tells you that your model performs quite well in terms of certain metrics, then we could apply code generation approach that assures you that the generated code also adheres to these quality attributes in the calculated manner by the dedicated view in the IDE. This brings me to the last slide of the presentation, which is a slide that collects some resources about Lemma, like publications with further details about our ecosystem, like for example is its initial motivation of language design, using Lemma in the domain-driven design of microservice architectures. We also have a methodology for Lemma-based SAR published under reference 38. If you're interested in the complete list of publications, please have a look at my DBLP profile. Lemma's source code is freely available on GitHub. We also have a documentation. It's currently work in progress, but at least we already have the installation details for Lemma ready there, and we also have a tool that you can use, sort of a tutorial to encounter the expressiveness of Lemma, constructing your own little microservice example. If you're interested in model processing, there is also a model processor example available on GitHub. We also have the static analyzer, the library, and it's executable on GitHub. And if you're interested in any more details about what I've told you before, Lemma's conceptualization or Lemma's implementation, please do not hesitate to send me an email so that we can have a further discussion there. Thanks a lot for your attention. And if you have any questions, please do not hesitate to mail me. Bye-bye, and thanks a lot.